Thank you, everyone. So for the next hour, I'm going to be speaking to you about quantum computing. It's a big topic to try to cram into an hour, including some question and answer sessions. So I'm going to try to do as best I can. But as Mario mentioned, I'm going to be here for this weekend. I'll be here all day today until 5, tomorrow from 10 till 2 at the booth right just outside of here, booth 95. So come by, we can go over more details. If you have any questions about it, if you want to actually run a program on a quantum computer, we can do that. If you bring your laptop, you can do it on your own system. If you want to take that information home with you, on how to compute some programs, I'll show you how to download our free open source software onto your computer. So as soon as you go home, you connect, you can actually continue working on any of our quantum computers. So to start, my name is Robert Loredo. As I mentioned, I am the quantum ambassador for quantum computing. Basically what that means is I do things like this. I come out, I do workshops, I talk about quantum computing. We do there's a bigger team, obviously, down in New York, a research center up there in Yorktown Heights, that does all the actual research on it. They do both the hardware and software, and then anything on top of that when we work with different partners. So what I'm going to be going over today is basically an overview of quantum computing to get you all up to speed. Mainly to how to get you to understand the reality of what we are, where we are in quantum computing, and then what potentials we actually have coming up in the future. So where we are right now in the beginning, we're pretty much in the beginning phases, right? So if you think of it in comparison to classic computers, which are the computers we're using now, on your laptop, servers, on your phone, on your watch, those are all different types of computation that were pretty much born on this. And what you're seeing here on the left is Colossus. That was our very first digital computer that was introduced back in the 1940s. As you can see, it was set up in a very large room, a lot of wires, a lot of tubes. This is before transistors, so we didn't have the bits as we know them now. They're using tubes. So they used this in order to program things back then. So where we are now is with this now our first universal quantum computer. And what that generally means is pretty much the same thing. We have a computer that can compute have some potential to compute some good potential, large potential calculations. We made it available to the public. One of the main differences between the two is that back here these days, you had to actually go into the lab. You had to go there and physically work with those systems. So before you got to do that, you had to be familiar with everything, right? So not everybody can just walk in and say, hey, I want to try it out. It was just too valuable a time back then to just do things like this. Whereas now, because of the internet, cloud computing, and all those modern technology that we have, because of the technologies that were born back in the 1940s, we can now not only have a quantum computer available to the public, but have it available to the public for free. Have it available so you guys can actually program on it. And and be able to use it and do research on it, right? So the reason that we want to do it this way is because one, it accelerates the research, right? One of our key things we want to do is make sure that this research grows, right? So it made more sense for us to let's just put it on the cloud, available to everyone. We have all our code is open source. Our information on all our hardware, qubits, are completely set up there, and you can access any of that information on the cloud, on our web. So. To kind of get you caught up, let's start a little bit of history. Not too much, but just a bit. If you go back to the 1920s, which is the picture here, this is back in Belgium, 1929, I believe, that they had a meeting with a lot of very important people in the world of quantum physics, etc. Some of them you might recognize. Right in the middle, you have Albert Einstein. Some names you might not be familiar with, but if you read a book about quantum, you'll know their names, like Schrodinger for Schrodinger's cat, Bohr, Niels Bohr, Madame Curie, who's third from the left there in the front row. So a lot of very, very, very important people. To kind of give you an example as to how smart this particular group was, 17 of the 29 people that are listed here, at the time or not that far in the future, each one of the 17 won a Nobel Prize. Madame Curie, who's the third from the right, is the first woman to ever win not a Nobel Peace Prize, but in two different fields. So she actually has two Nobel Prizes. So fast forward from the 20s up to 1980s. In 1981, MIT and IBM had a conference, particularly for the physics of computation. And this particularly was, how can we use now what we learned in all that history of theory and evolution of the experiments from quantum mechanics and quantum physics, how can we use it now to come up with what we call quantum information science, in a sense. So this picture here was the first conference that they've had, which is a combination of IBM and MIT. And in there, one of the, a lot of very well-known folks, but at the very top here on the corner is Richard Feynman. Richard Feynman was a very popular physicist. If you know anyone who's a physics major or a physicist, and you can pretty much guarantee that in their book collection they're going to have Feynman's lectures, because this is almost the standard of within physics. And in there, it mentions a lot about quantum physics. One of the things that he mentioned during this particular presentation is that nature isn't classical. So we're talking about quantum computing. You can't. Classical computers, as we know, are not going to be able to simulate. If you want to simulate nature, you have to make it quantum mechanical. And he added there by saying it's a wonderful problem, but it's not easy. And there's a big phrase in there. It's a wonderful problem because there's a lot of potential in it, but it's not as simple as when we discovered classic computers. Now, what did he mean by that? So, I think a good example I like to use is caffeine. We're all familiar with caffeine. We drink our cup of coffee, it's got caffeine. You take a soda, it's got caffeine. Pretty much almost take anything, it's got some form of caffeine in it, right? So it's basically this thing that gives you energy in a sense, right? So if you want to represent, and I highlighted in blue there, if you want to just represent one molecule of caffeine, which you can see here, that's the chemical molecule for caffeine. You can see there's a nice cup of coffee there. If I want to just represent that molecule, and represent doesn't mean just draw it. It means how do the energy levels between the two molecules push and pull against each other. If I want to just represent it, not model it, but represent it. Model it means how does that one caffeine mixed in with the billions of other molecules of caffeine in there interact with that cup of coffee, which has other molecules. And when I drink that cup of coffee, it gives me a headache maybe because I got caffeine rush or caffeine withdrawals, right? So all that is millions and billions of other molecules that I have to now figure out how they interact, right? But eliminating all that, we just want to represent one molecule of caffeine. With a quantum computer, I can represent that with 160 qubits, right? Qubits is quantum bits. It's the quantum computing version of a qubit. Does anybody want to take a guess as to how many bits on a classical computer would take to represent just that one molecule on the size? Yes? 160,000? Very close, very close. To be exact, that's going to take, and this is a scientific number, but let me give you an example of what that is. 10 to the power of 48, which is a 1 with 48 zeros past it. So it's a little bit more than what you guessed, but it's a very good guess. It's a very, very good guess. So to give you an example, how big is that number? Pretty big. To fathom it to other things, to give you an example, 10 to the power 49 to about 10 to the power 50 is how many atoms there are on this planet, right? So basically it means 1% of all the atoms you got to collect just to make a computer big enough to have enough bits to be able to represent. That's, again, representing. That's not modeling or doing a lot of other stuff. That's just one molecule, right? So you can see that there is some kind of limitation to what we can do on a classic computer versus what we could do on a qubit computer. That's just for caffeine. If you look at sucrose or penicillin, there's obviously a lot more, right? And again, this is modeling a single molecule. Now, if you want to look at, representing, a single molecule. If you want to be able to model it and figure out what it does with other molecules, how it interacts with other molecules that interact with other molecules, obviously you're going to need a lot more than that, more than we can build. So from a physical perspective, scalability, there's obviously going to be a big difference here. So what do we mean by modeling a molecule? As I mentioned, here's naphthalene, basically 116 qubits to represent that. In classical bits, 10 to the power 34. To give you an idea what that is, in 2014, there was only 10 to the power 25 bits of information on the internet back in 2014. So you can imagine how, obviously that's a lot of information you need to process, right? And to get an idea as to what they mean by modeling is something here you have you can pretty much see this is how they react, right? This is one particular representation of the way they act. So you can see the molecules, how they interchange with each other, how they move around, how they stop. So this is just for the represent. Now, if I add another molecule below that and see how they react, again, that adds a lot of computational power, right? And that's just not feasible with classic computers that we have. So there's that potential with quantum computing. So what we learn from that is that with quantum computing, we have something called exponential growth, which means that for every bit of information that we have, we're increasing our basis states. What does basis state mean? I'm going to get a little bit into that in a little bit in the future. But basically, it means for each qubit, I can have, in classic computers, works on zeros and ones, right? It's either a zero or it's a one, right? So we have a single basis state here. Here we have two basis states, but it means that a quantum computer, it could be a zero, it could be a one, but it could also be a combination of the two. It could be a little bit of zero, a little bit of one, right? So now I'll go over what that generally means. So for every qubit we add, we're adding two basis states, right? So if one qubit, I have two basis states, which means I can be 0, 1, or both. If I have another one, I can be a one of 4 different basis states. Now this is at the same time, not one or the other. If I have 3, I now have 8. So basically that means that every time I add a qubit, I'm increasing the number of terms. So to give a perspective, if I have 1 million classic bits, and I want to double that, how many more bits do I need? Double the bits. right, of n, power n in a sense, right? So if I have 1,000 bits, I want to go 2 times fast, I need to add another 1,000 bits. If I have 1,000,000 bits, I want to go 2 times as fast, I need 2,000,000 bits. Quantum computer, if I have 10 bits, 10 qubits, and I want to double it, I just add one more qubit. If I want to double that, I add another qubit, right? That's what this means. That's what we mean by incrementing. So our computational power is exponentially grows with every qubit that we add. So here's an example. We kind of see in the beginning, not too much of a difference, but once you start looking down here at about 35 qubits, now you go into 100 qubits, it's more atoms than we have on the planet. 280 qubits, more atoms than are in the entire universe. Right? And that's just 280 qubits. Let's think about that in terms of if we're talking about bits, 280 bits. Right? So eventually, hopefully, we're going to get to 500 qubits, 1,000 qubits, 1,000,000 qubits, 10,000,000 qubits, 1,000,000,000,000 qubits, a gazillion qubits, right? So it keeps incrementing, and we just keep adding them. We keep incrementing what we call quantum volume, which I'll get into what that means in a second too. You can see that the computational power grows exponentially. So now we can do a lot more things. We can solve problems that we couldn't even think about solving with classic computers now, just because of the fact that we can't build a system to be able to compute that kind of information. So what does the potential open up here? Obviously, in a lot of things. Chemical and petroleum. We can do, obviously, chemical design. How does caffeine react with my body? If I get a headache because I'm having caffeine withdrawals, I'm trying to cut down on caffeine, how can I figure out how best to cut down on that, right? So you can look at that. Financial services, right? Pretty much anything you can compute. So we can compute things like risk assessment, targeting, portfolio management. So a lot of finance areas looking here. Life sciences, drug discovery, precision medicine. Again, if we all went out drinking tonight, we all had exactly the same amount to drink. Tomorrow morning, we're all going to wake up with the same headache. However, I have a friend that as soon as we wake up in the morning, he can go out and relax and act like a normal day. I'm sitting in bed for 4 hours trying to recover, right? So there's obviously a difference. If he takes a Tylenol and I take a Tylenol, it affects us differently, right? But how can we determine? How can I know exactly how many milligrams of Tylenol to take, for example, and my friend will take that will pretty much be at the same level, meaning the same effect, and my body will react to it with what his body will do. So it's personalized medicine, for example, right? Precision medicine. Manufacturing, supply chain. How can we get products to move along easier? Now we have the 5G, right? That's a lot of information traveling. How can we get that information to be more optimal when you're transferring it with data? Transportation and logistics, right? Customer behavior, dynamic pricing simulation, digital logistics optimization. All these things you can look at handling with this. One that's not here is on security, right? Cryptography. There's a lot of talk in the news and everywhere about quantum cryptography. How does it affect this, et cetera. As you plan early, you'll be able to, security is always going to be a problem, with or without quantum, right? You hear about it all the time, people getting hacked and this and this. As long as you have a plan for it, you know what's coming up, you know what you can and can't do with a quantum computer. There are systems now that can handle the kind of risk that quantum could have. You can solve that on a quantum computer. But there's also cryptography is being developed that's called post-quantum cryptography. They're using those exact same systems to come up with different cryptography models. I mean, security is always going to be a constant evolution, right? So that's always something we want to look for. Back in September 2017, again, we published an article kind of looking at the potential of quantum computing. Right? Here we talked about the chemistry. We were able to represent two molecules, lithium and hydrogen, and see how they react together using quantum computation. So we talked about that and obviously what other areas that they might go into. At the time, we figured it would take a few years before this thing actually spit up. But because since that time we had the quantum computer open to the public and there was a whole lot of research going on in it, the research actually grew so much that a lot of the advances that we thought was going to take longer actually took a little sooner. We were finding some ways of boosting quantum computing and machine learning. So this article, just 18 months after the original one that we wrote, came back on Nature talking about just that. We've also had other articles on finance and optimization. So there's a lot of research being done that's going to be coming out, mainly because there's just a lot of activity and a lot of growing interest in research. So now that being said, where are we in quantum? You hear about it all the time, people saying, oh, quantum is here, it's time to throw away your laptops, quantum's here, go buy your laptop, you go to Best Buy, you'll be all set, everything will be fine. No, we're nowhere near that. So here what we came up with in a sense is a sort of different phases or eras, if you want to refer to them, on quantum computing. In the beginning, you can see around 1900, which pretty much started around that, where I showed you the initial picture of Einstein and the other physicists. That's pretty much where the fundamentals began, right? What is quantum physics? What is quantum mechanics? What kind of features can we do? From there, we grew up into the quantum information science, right? Okay, how do we use this information to actually compute something? So in 2016, May of 2016 to be exact, IBM launched the IBM Q Experience. So this is basically their first quantum computers. It was a 5-qubit and a 16-qubit quantum computer. They put it on the cloud. They had software available to be able to program on it. They had tutorials. They have tutorials there on how you can use them to solve different types of problems. A lot of stuff, all the research papers that were published are listed there. So basically we put it out there because we said, look, here it is. We have a quantum computer. If we want to accelerate the research, here's what we have. Here's what here it is. Here you go. Go for it. Right? We could have locked it in a room, put 10 physicists, PhDs in there, and said, okay, figure it out, then we'll show it to the world. But figure that's going to take us back to the history of the 1940s. Why repeat history exactly the same way it is? Why don't we advance and make it a little better? We have cloud, we have computing, we have a way to access things. Let's make it available. Let's just work on accelerating the research, get everybody involved. It's an exciting area. I'm glad they did because that's how I get involved. I wasn't a PhD researcher working deep, into the machines. I was a developer, an architect. But I have background in quantum from the university. In fact, when I went to college, they were telling me, quantum computers are way in the future. So I was like, okay, fine, I'll just focus on the classic computer stuff. Then lo and behold, here it is. So I blew the dust off of my quantum books, read up a little bit on it, studied what they had done, and now I'm here as an ambassador talking to you guys about it. So things just accelerate through this technology. It's great. So we're right about here with this quantum ray, which is just that. Let's understand it. It's obviously different from classic computers, and I'm going to go over a little bit here so you guys can actually understand what that means. But basically, it's a way of understanding how can we use these quantum principles of superposition and quantum and entanglement in a way to program, because it's not lift and shift. It's not, okay, let's get our algorithms on quantum, just dump it in a quantum computer and we're set. It's nothing like that. It's completely different. Right? You saw some of the differences there are. So this is what we're doing now. We're researching things. People are open source, contributing pieces. We're working with different companies who want to focus on particular areas. So we're doing all of that right now. So we're eventually getting ready for what we're calling the quantum advantage phase. This is the area basically where you're going to get to something that's called a universal fault-tolerant computing system. What does that mean? Right now, you'll probably read about it, what we call noisy intermediate scale quantum computers, NISQ. And basically that's what they are. They're small, they're noisy, 5 qubit, 16 qubit. And noisy means, because at that subatomic level, anything I do is going to introduce some noise. So even just taking a measurement introduces some noise, some error. So that qubit wants to move, but as soon as I touch something, it might shift a little bit different. To give you an example, just imagine you have a bowl of water. And in that bowl of water, you're going to put, likely press right there, a marble. And it's going to float right in the middle. Half the marble on top is white, let's say, no, bottom part, half of the marble is black. So if I tell you, using your finger, just touching that marble once, you have to hit it in such a way that the marble will flip completely 180. And obviously it's going to put some ripple, there's your noise, and stay exactly that way. Not a little bit, not rolling around, but just do it with just that one shot. That's what has to, in a sense, happen with the quantum computing. If I want to flip that qubit from 0 to 1, I have to do it in such a way that it'll flip and land exactly where I want it to land, or at least where I hope it'll land, and without introducing any noise. In other words, if I hit it too hard on that marble too hard, it's going to shift around out of the middle, or it's going to, that bowl of water is going to start creating some ripple waves, which is noise, and then the marble's going to spin around, and it's not going to be 50 up, 50 bottom. It's going to be rolling around, right? So we're trying to perfect that so that when we get these particular computations in there, we know it's exact, or at least close to it. Right? Once we get to that, we're able to demonstrate that there's an advantage to a quantum computer to a classic computer. And by that, I mean either I'm computing something that's physically impossible, as we saw, like modeling caffeine, that you just can't do on a classic computer, or I'm doing something that's called quantum speedup, meaning I can do it faster on a quantum computer than a classic computer. And by that, I don't mean I'm doing it twice as fast. If I do something twice as fast, I would think, all right, I have a classic computer, I'll just run mine twice as long, big deal. I want to run it 1 million times faster, 10 million times faster, 1 billion times faster, so fast that it's pretty much, there's just no way you can do that on a classic computer. Right? So when we get to those particular things, we're at this quantum advantage, meaning by then we understand how we program it, now we have a machine that can actually do it, and now we're ready to go, boom, you take off. You move from here to here really quick. And then you can go into things like enabling science discovery. You can obviously extract some commercial value. You can actually use it for different things. So all of that stuff will get us there. So this is where we're trying to get to now. So this is where we are now. The computers we have now, a 5 qubit system, 16 qubit system, you can't do anything there that you can't do on a classic computer or a supercomputer. But what you can do on there are some experiments that you can't do on a supercomputer once these systems get to that scale, right? So that's why, hence, the quantum ready phase. So, we mentioned qubits. What actually is a qubit? So a bit, as we know, has 2 states. So if you imagine my hand here, it's either a 0, as you can see by the North Pole, or it's a 1 in the South Pole, right? So it means in a classic computer, it's either up or down, true, false, yes or no, whatever, right? On quantum computer, we have something called superposition, which enables me to be in both states at once. Now what that means, it doesn't mean from a graph perspective, yes, it means I'm somewhere between 0 and 1. So you can see this little angle theta. I don't mean to throw too much math in there, but some angle from one of the poles out from center. If I'm perfectly up north, I'm at 0. If I'm perfectly down in the bottom, I'm 1. If I'm here, I'm between 0 and 1. But if I'm here, I'm also between 0 and 1, but just a little more 0 than 1. Same thing here. I'm a little more 1 than 0, but I'm still somewhere between 0 and 1. That's all it is. The second one, this little phase, is that I'm not only looking at it from the North Pole to the South Pole, like this is in the middle, but now I have phase. I can now be in the middle, but anywhere in between here. So this allows me now to have every single point on that sphere, basically, anywhere in between or any phase. Every point in this particular graph on my thumb is a point that I can calculate, compute something on, right? Hence the difference from classic computers, right? So this is what I mean by superposition. And again, by meaning 0 and 1 doesn't mean I'm in some weird state. It's like, think of it as a map. If I tell myself I'm going to move 2 paces north, 1 pace west, I'm not saying, well, look, I'm north and west. No, I'm just a little north, a little west from where I am, or just west of the North Pole or something. Right? So I'm at some position. That's basically all this is, hence superposition. Right? So quantum computers take advantage of these mechanical principles. So superposition means I'm in a state of 0 and 1. The other principle is entanglement. So to explain entanglement, I'm going to give you a very not exact scientific, somewhat scientific, but it's not the exact scientific of what superposition is, but it helps explain what it is, what this is, in a very easy way to understand. Superposition, so if you think if I have a coin, a quarter, a nickel, a penny, and I spin it here on the table, it's spinning right now, right? So if I ask you right now, if I collapse it and measure it, how many of you think it's going to be heads? How many think it'll be tails? If I do enough spins of this in experiments, by probability, it'll be 50-50. It means half the time it's going to be heads, half the time it's going to be tails, right? So while that coin is spinning, at that moment, it's in superposition. It's either heads or tails, we don't know yet. It's not until we measure it and look at it that we can say, okay, it was heads or it was tails, right? Now, that's how superposition comes in. It means at that moment, it's taking both states. The difference is that as soon as I collapse it, in other words, as soon as I measure it, I see, aha, look, it's heads. All right, great. Now, let's calculate something else so that we can't anymore. Why? Because now it's no longer in position. It's at tails, it's at heads, whatever it collapsed to. So I can only pick it up and start over again. But that doesn't mean that that's going to be the same. So in that sense, as soon as you collapse it, as soon as you take a measurement, whatever point I'm in on that state, it's going to collapse to either 0 or 1. The reason it collapses is because I'm reading it into a classic computer, and the classic computer only knows 0 or 1. Right? So that doesn't help me, because if I take a measurement and I see it, okay, I can't continue my experiment, which doesn't make sense. It means I'm going to do this to a qubit and then say, okay, let me some information I can. So that's where entanglement comes in. So entanglement says, if I know that 1 qubit is 1 value, it's going to collapse to 0, collapse to 1, I know that this one's going to be exactly the same. Meaning we have 2 coins now. I spin one, I spin the other. And I collapse one, and I look at it, and it says heads. I know that those, even if I collapse at the exact same time, or I wait an hour later, or a week later, or a month later, when I collapse it, it's going to be the exact same value no matter what, because those 2 qubits are entangled. What does that allow me to do? Now I have 2 qubits spinning. If I need to find out what state am I in, I can collapse one, see, okay, it's heads, since it's, or 1. So if it is, then let's continue the experiment with this qubit, and I'll entangle this qubit with another qubit, and then run some other experiments and measure it, measure with another qubit, and measure it. So we're going to keep going down until we can keep using entanglement until we run out of qubits and before we finish our experiment. Right? So this allows us to be able to do 2 states, and this allows me to measure anytime I want a particular state, and then use that information to continue calculations in both states, 0 and 1. But I know pretty much where. So here I can say, okay, if 1, then do this with this qubit, or if 0, then do this with this qubit. You could do logic like that. So there's different things you can do. So it's because of this that we have that extra feat that normally you don't get with classic computers. Now, qubits, and that's usually the question you normally hear. All right, how many qubits before I can do this on the classic versus the classic computer? How many qubits do I need to do this? How many qubits do I need to do that? Because quantum computing is on different principles than classic computers, so is the availability, the capacity of being able to calculate things. With classic computers, it's bits. If I have more bits, I have more processing power. Right? With qubits, it's something called quantum volume. And quantum volume is made up of 5 different characteristics of a computer. One of them, obviously, yes, it is the number of qubits. If you have more qubits, like I mentioned, you can entangle more things, you can do more calculations, etc. So yes, that is one of the parts, but it's not the only thing. The other thing you see is connectivity among qubits. Remember I mentioned entanglement is important. So if I have 5 qubits, and qubit 1 is to 2, 2 is to 3, 3 is to 4, then that means I can only calculate a certain way. But if all qubits are connected to each other, then I can entangle and do a lot of calculations any way I want. So it makes it easier for me to program something. So connectivity between qubits. How many gate sets, how many operations can I run on this qubit? Is it only just flipping it once and then put it in the middle, or can I do phase shifting? What kind of operations can you do? And the more important one here, I think right now, because we're in these noisy intermediate systems, is error and decoherence of gates. Meaning that qubit, if I tell you right now to hold this very light clicker, hold it on your hand and keep holding it there until I tell you to bring it down, I can stand here for a good hour maybe, right? But after a while, my arm's gonna start getting tired. It's gonna start straining because it's holding this thing up, and then it could be anything, but eventually you hold anything long enough, your arm's just gonna get tired, it's gonna give up, right? And that's pretty much the same thing with qubit. Qubit wants to be able to go back to that excited state. It doesn't want to stay in a state where it's at, right? So you can only do so many operations, and as I mentioned, if you make an operation, that introduces more noise too. So if I have a qubit and I put it in the middle, and I do some more operations, it's going to start vibrating. So if I pick to measure now, it's going to be closer to 0, it's going to clap to 0. But if it's vibrating and I say, no, I want to take a measurement now, it's closer to 1 than it is 0. So this error rate is giving me might introduce some noise. It might give me a whole difference between 0 and 1. So the less error I put in between, the better. So decoherence means I can do more operations on a qubit, more time I can spend on a qubit doing a lot of things before that error becomes a problem. So if I can only have 10 microseconds or 50 microseconds of work before that noise is too much that it just starts to act like a classic computer, then that's no good for me, right? That means because it's a short amount of time, my algorithms might take more time, right? So I need to increase that error rate. So by increasing it, I can increase my capacity. So here's a graph, for example. You can see here on the x-axis, there's the number of qubits. So we have 5, 15, 50, 100, 200 qubits. And here we're going from a very high error rate, 0.01, to a very low error rate, 0.00001, right? So if I have 50 qubits and the error doesn't adjust at all, if I double it, you can see my computation power doesn't grow much. It's about the same. So I don't increment anything by adding another qubits. So if I have 50 to 100, no increment. From 100 to 200, nothing. 200 to 500, nothing, because I have too much error. It means, yeah, I have 500 qubits, but I can only calculate so much, so I can't do too much with that, right? But notice, if I just improve the error by 10 times, or 100 times, you can see that the computation power with just 50 qubits more than doubles, right? Because I can do a lot more computation now. Now, if you look at 50 qubits with a low error rate versus 100 qubits at the same bad error rate, I can do more with less qubits because I have more quantum volume. I have more connection between qubits. I have more coherence time. I can do a lot of more operations on it. I can do a lot of parallel operations on it. How many qubits can I run calculates at that exact same time? All that stuff comes up and computes this quantum volume. So whenever you hear anything, how strong is the system? Our system has 5,000 qubits, 1 million qubits. Okay, great. Now, how many operations can I do on them? How are they connected? What's the decoherence gate? The error, right? How much error do you have? That's when you really know how good the system is. It's not just number of qubits. Here's just some numbers pretty much. They kind of take with a grain of salt. They're just estimates more than anything on running different things. Pretty much they start around 100 to 1,000 qubits down to the millions of qubits. So that's a qubit. Now the hardware. What is a quantum computer? How does a quantum computer work? What is the physical difference between a quantum computer? So here you can see on the left, top left, this looks like a chandelier. It's actually our dilution chamber. It's what we use to cool the qubits. So in order to start the qubit, they have to be at an initial state of 0, which means we got to put them at almost 0 degrees, absolute 0. In other words, they can't move. So you can see by the different levels there, we started at about 40 Kelvin. Then we dropped to 3 Kelvin, 0.9 Kelvin, 0.1 Kelvin. At the very bottom where the qubit actually resides is 15 millikelvin. To give you an idea as to how cold that is, it's about 10 times colder than space. So that's how cold it is. 0 Kelvin is absolute 0, means nothing, not even bacteria, nothing, no atom moves at all. It's just, that's why they call it absolute 0. So 15 millikelvin is very, very close to absolute 0. And the reason is because the qubits, here you can see the superconducting chip with the qubits in there. We need to cool it that way, so that way that initializes that qubit to just sit still at 0. And at that point, then, we can do our calculations. And how do we do that? Well, I'll show you. Wrong way. So We start over here with our users, whether you're a quantum physicist, chemistry, you're an aviation expert, or pretty much you're any kind of scientist or some researcher that you want to run and program on. You start from there and you have a connection to Qiskit. Qiskit is basically Quantum Information Science Kit. It's our software kit that we have open source that you can use and program and integrate with your programs and actually send information to get calculated on a quantum computer. So that gets sent down to a classic computer we have on the cloud or Spectrum. So that does all the pre-processing. So it gets your calculations and turns them into pulses, mechanical functions. So it's going to go into this system. Like here you can see it's a rack of basically different switches and pulse generators. And from that, it goes up. You can see through the blue line at the top goes into what's called a connector. And that connector basically sends a signal from our classic systems, our server racks and microwave generators, sends those pulses through an input module. That input module is basically cables, filters, very small things that basically sends, like I mentioned, that little pulse of electricity, energy down there, microwave pulses, all the way down to the quantum processor, which you see down here. And what it'll basically do is one of two things. It'll tell it, do this, do that. In other words, flip from your axis you're on, or go to Hadamard, which in a sense is going to in a combination of 0 and 1. Whatever pretty much your computation, your program tells it to do, it's going to program it down there. Once it does, then the second thing you can do is you take a measurement. You can say, okay, tell me where you are, or let me find out what state you're in. Then that information gets pumped up. So it goes to an amplifier, because obviously it's a very, very small atomic level, so you got to take a reading at a very high frequency. So you need to amplify it and bring it up in a way also that doesn't introduce noise. So that wire is going to be completely clear. So you go up to the output module, back to the connector, back to these racks, the same racks that wrote the stuff out. It's going to receive the information, convert it now to your classic computer bits that you know is 0 and 1, and bring that back over to your results. So when you get the results back, you now have the results from the quantum computer. So that's pretty much how the system goes back and forth. That thing you see at the top looks like a big tank. That's the cryogenic chamber. That's what pumps this chandelier. We normally see it open, but we generally cover it in a tube, and that's basically to keep that whole chamber completely cold, and that's what we use to drop the temperature. So the way it works, at the very bottom you mentioned, this is the dilution chamber. It's in this chamber at the very bottom that gets down to 15 millikelvin, so that's very, very, very cold. You can see all those little things we have in it that look like little rings. Right? Does anybody want to take a guess as to why we designed it that way? So when we have this open, in order to maintain it, it's got to work at room temperature. I mean, we have to be able to get in there and change the qubit or maintain it, calibrate it, etc. So it's got to operate room temperature. But as soon as we close it up and turn it on, it's going to drop to that extreme level. So what happens to metal and all these things, when it goes very hot and very warm, very cold, etc., it expands and contracts, right? So what happens? If this thing were to be a complete straight wire, when it compresses, it'll break, right? So it's designed that way, so that way when you see those little levels, they basically will also compress and contract. So they want to be able to do that in a way where it won't break anything, one, and two, that if it bends, it doesn't introduce any kind of noise, right? You don't want to make it growing long or short because that affects it. Think of it as like a piano string or a guitar string. If I just play it, it's fine, but if I go there and I extend, that's noise. It's not the right note I want to hear. So you have to make sure that when this thing compresses and decompresses, it still stays attuned to that, because otherwise when we send a signal, it's not going to work. Right? So even the design of the way we have everything set up was all engineered. There's nothing here that wasn't engineered or tested at any time. And again, this is the quantum experience. So you go on, if you Google IBM Q Experience, you get to see a lot of the code and everything that we have. You can download. Qiskit, as I mentioned, is a quantum information science kit. So this is pretty much what it's made of. You can see you got the hardware and the Qiskit realms on the top. Basically what it is Qiskit Terra is what we use to program directly to the system. It's what takes your code and collects those. It knows if you want to flip a gate, a qubit on its axis by pi, flip it from 0 to 1 or 1 to 0. Terra is basically the code that you write to do that. There's these other pieces that we put on top, Ignis, Aqua, and Air. Those are pretty much written on top of Terra so that a researcher, who's a researcher in AI or in chemistry or finance or optimization or anything that's not quantum, they can use it without having to know how to program a quantum computer. So you say, all right, you have a quantum algorithm that can calculate, support vector machine, or you have something that can calculate some optimization pattern like a Marco Polo or Monte Carlo optimizer. then I want to use it. I just want to give my data, you run a computer, and then give me back the results, that's all. Aqua is built for that. Basically, it's just from your code, whether you're using Jupyter Notebooks or some Python code, somewhere in there you have this data. I just collected, I prepared it, I know what I have with it. I want to compute something with using a quantum algorithm. You send that information back, get results, and then you can do that. Air and Ignis are basically different things. Air is if I want to be able to call different backends. If I want to create my own little simulator, I could deploy it, say here's a simulator that simulates chemical reactions or something. Ignis is if error correction, right? So like I mentioned, sometimes there's these errors that happen on the qubit. But you can mitigate those errors, one obviously on the hardware, cleaning up some of the hardware, filtering it, etc. Another option can also be is be able to do that from a software perspective. If I know that at certain times when I want to, if this thing is supposed to be right in the middle, I know that after this amount of time, I'm going to get some swinging. And if I can understand, if I can get a model of what that error looks like, I can then write code that could do some error correction, hence error correcting codes and things like that. So we actually have things in their research that's going on in those aspects. So if that's an area that you're interested in as well, you can get in on that. So this is pretty much a screenshot of what we show. So we talk about the software and what it's made of. Well, let's say you want to actually write a program. So we make sure that we give you all the information. Like I said, we're not hiding anything here, right? So you want to see, okay, how is that qubit connected? Remember I said connection between qubits? That shows exactly which qubit is connected to which. It tells you when it was last calibrated. It gives you all the information for each qubit, qubit 0, 1, 2, 3, 4, so you can see all that different data. And then, so when you practice it, when you're actually using it, something like this, you would do, this would be pretty much your set, right? If you're a chemist, you want to be able to model lithium hydride, you set up your molecule, you calculate some energy, you pass it to the quantum computer to do some calculations, you can iterate as many times as you want, and then once you get that all completed, you can get some post-processing, so I can get that information and then look at the dipole moment or the excited state, the ground state of all these molecules. You can actually run this right now in a tutorial. Like I mentioned, we have a booth out here, so if you want to try it, if you have your laptop, we can actually run through this, and you can actually run this exact same experiment on your laptop computer. Obviously, it's going to be connected to a quantum computer, so you'll be actually programming on a quantum computer. It's pretty much an idea to all the different researchers that's going on. Every bubble that pops up is pretty much an experiment that was run. I think I ran this back in May, or maybe March earlier, I'm sorry, March of this year. But basically it's running on our Q of 15 and 16. You can see it's hundreds of thousands of users, all 7 continents. There's actually a researcher in Antarctica who's doing some research, and she wanted to try running an experiment on a quantum computer. So she did that and published it, so she's one of the 100, now we're actually up to about almost 150 to 180 research papers that are out. One of the important things we're trying to do is, obviously, it's not an easy area to get into. It's a completely different way of thinking. So there's a lot of research going on, but then there's also the need for educating, right? It's not something you learn. A lot of the research that we're doing basically is just on that, on how we can use it on machine learning, in chemistry, optimization, for example, quantum risk analysis if you're in finance. So in order to do this, we've partnered already with a lot of companies. We're still getting a lot of firms coming in to work. From a hub perspective, these are basically universities that want to partner us directly. They're saying, listen, we want to get your most latest and access to the most latest systems you have, because we want to base our research with either other grants that we do with government agencies or with companies, and we want to be the sort of hub for quantum computing. So North Carolina State is in here, Care University, Japan, University of Oxford, Oak Ridge National Laboratories, we talked about that earlier. We also have some partners, like JP Morgan Chase. They're looking at ways of optimizing finance and these kind of things, right? Samsung for electronics, Daimler for transportation, ExxonMobil, latest came up and they announced in January they're working with us on energy. And for academics, obviously just being able to teach quantum computing in general, right? So you have University of Minho, MIT, edX, University of Taiwan. CERN recently came in wanting to work with us. They want to be able to see how they can use this with their particle accelerator. Different members you have that pretty much come and just want to use their Fermilab, just recently came on board with us on there. And of course, startups. There's a lot of companies that are just kind of just want to get started. They want to see how can you use quantum maybe make it better. If I know that I have sensors out in the field right now, for example, that are pulling in data, but they're sending information to a classic computer, maybe they want to optimize it in a way where if we know that this data I'm pulling in is going to a quantum computer, let me prepare the data in such a way, right? So there's people that are looking at those kind of things. So all of those are different startups that we're working with, and obviously this Q network that we have is expanding every day. ExxonMobil I mentioned was recent. So Over the past years, I mentioned in 2016, we released our first quantum computer on the cloud. It's a 5-qubit machine. You can see the processor there. 2018, we extended it out to a 16-qubit. We actually right now released this year our first universal quantum computer. It's basically not universal, sorry. Our first commercially integrated quantum computer called the IBM Q System 1. So basically, we're taking now the computer out of the lab. So if you remember the very first picture we had with Colossus, we had a picture of a big computer inside of a big room, like a room like this, a research lab. Now we said, well, let's make it commercialized in a sense, right? So we put everything that was normally just within a room, it's now contained in a box you see here. So what you're actually seeing here is what we have, right? That dilution chamber in the middle. Behind it, you see that black box in a sense. Back there is where we have all those racks of systems and wave force generators. At the very top is the cooling system. We use to cool the qubit down. It's on a raised platform, so that way it eliminates any kind of thermal heat and vibrations that might introduce noise and air. The glass is tempered, so it's soundproof, heat-proof, so we don't get any kind of thermal interference in there. And of course, it's all easy to maintain, so that the glass on the sides can open up, so you can push one machine out while pushing the next one in. So we can take one out, maintain it, upgrade it, calibrate, whatever we need to do with it. And at the same time, a new one will come in. That way our maintenance and our downtime of our servers are very, very low. Right? And that was designed a certain way because if you think about it, if you get a box and you take out 2 sides of a box, that box is going to fall to the side. Right? So it's designed so that you can take both sides out, move things around in there without having the whole thing collapse. So that takes me down to a video. Actually, there are 2 videos back to back. The first video you're going to see is the inside of a quantum computer, the one that was in the lab. And that one, you're going to actually hear the noises of it. So when you hear, it's actually, the quantum computer is quiet, it's silent, there's no noise in it. What you're actually hearing is that dilution chamber cooling that qubit down to almost absolute zero to make it when it was cold in space, 15 million Kelvin. And you're going to see all the insides, all the things that kind of connect to it, etc. Then the second video is going to start right after that first one is the current one I'm showing you now, which is the IBM Q System 1. It's that integrated system. There you'll actually see the qubit, the most latest one. It's a 20 qubit, 4th generation qubit. Reason it's 4th generation and we come out with a 50 qubit is, as I mentioned before, quantum volume, right? If I just add a 50 qubit to a noisy machine, as you saw in the quantum volume slide, we're not adding anything. So you're not getting anything out of it. So 4th generation we did a lot of noise. We did a lot of things to reduce the noise and it makes it a lot more coherent. We increased the connectivity between the 20 qubits, right? So a 4th generation 20 qubit is obviously a lot more optimal. So once we got the noise figured out and cleared out, now we know, okay, the next step is, as I mentioned, the quantum volume, number of qubits. So when I add number of qubits, now I'm adding quality qubits to this. All right. So with that, we'll show a video, then I'm going to introduce a colleague of mine, and then we'll open up for questions. But that's much. So with that, before any questions, so one of the things I mentioned is we obviously do a lot of work with different universities and things outside. So about maybe about 2 months, maybe 3 months ago or so, one of our directors reached out to me and said, hey, there's somebody who's interested in learning about quantum in the area. Would you be interested as a student from a local middle school? I said, sure, of course, why not? It's local, may as well help out as much as we can. So I reached out to him, we had a couple of conversations, we talked about, just I did what he wanted. He's actually working to do something for a science fair at a school. He wanted to do it on quantum. So I said, okay, what, I thought it was high school for some. I said, okay, what, the senior high school? He said, no, middle school. I thought, what? So I'm thinking, okay, because I'm thinking when I was in middle school, I was playing with Turk probably, I don't know. So, but so I was very impressed, and he was very knowledgeable already, just basically on the stuff that he saw online. Like I mentioned, we have a lot of stuff you can learn online now. So with that, I want to introduce Dylan Parsons to come and maybe say a few words about what he's learned so far. So Dylan.
Thank you. As Mr. Loredo just said, my name is Dylan Parsons. I'm currently an 8th grade student. I'd first like to thank you for helping me out these past few months with this. And I'd also like to thank IBM for their commitment to educating everyone. So I first started out by learning about quantum just by finding out through it on the internet. So I saw an article published about it and was like, hey, this looks pretty cool. So I decided to look into it a bit more, and then came across videos from researchers, like he said, Dr. Talia Gershon, and where she explained the beginning, basics of quantum computing. And from there, I started, actually picking up articles about it, and then, heard about how IBM was actually trying to utilize this technology to use it for a real quantum system. From there, I had the science fair assigned, so I said, hey, it would be really cool if I could actually integrate a quantum system into a science fair project. And from that point, I contacted Dr. Talia Gershon in Yorktown Heights, and she referred me to Mr. Loredo, who helped me build my science fair project, as it is right now. After reaching out, Mr. Loredo helped me better understand quantum by giving me lectures on it through online lectures. And from that point, I also just started picking up more articles, and through the IBM Q experience, they offer a multitude of articles about both community published and also published by IBM themselves, which is a very useful helping resource. And IBM has introduced so much into making sure that everyone can be as educated about this as possible. The experiment I'm doing right now about quantum is currently about assessing error rates within quantum computers and seeing how a quantum computer compares to a computer today, classical computer, which currently, obviously, the classical computer would win because error rates are still pretty high for a quantum computer, but as System 1 greatly reduces those error rates. So I was testing on an older machine, so but what I plan to do for my future, when I progress my quantum understanding, is I hope to bring it to a larger scale application, to maybe to see how it can be used for chemistry or simulating nature, and try to solve a real bigger problem with it. And really just to sum it all up, I'd like to say anyone can really get started with quantum. I got started with it a few months ago. I had absolutely no knowledge about any of this, and I'd just like to say anyone can get started at any time. And with that, I'd like to hand it back to Mr. Loredo.
All right, thank you. So we got about a little 5 minutes or so open it for any questions you guys might have. Anything at all?
As you transition to a quantum future, obviously there's going to be classical computing and quantum computing coexisting.
Correct.
how will we address the security issues that will arise for the classical computers when quantum computers are online?
Right, that's actually one of the many questions, one of the questions we get most of. And just like anything, it comes down to a plan, right? Even before a quantum computer, if you have a system and you have certain compliancy issues, right? If you're doing medical research or you have privacy data, or just customer data in general you don't want to have just out there, you should always have some kind of security plan in effect, right? That security plan should look at not just, hey, are we safe now, we're good? No, it should be looking at what's coming up, because you never know. The idea of any best security plan is being one step ahead of the bad guy, right? So, granted, that being said, having a good security plan is important. And with that, there are classic systems that you can use that can defend against those kind of attacks, right? They exist now. So, probably the one that's usually being called out on is the algorithmic Shor's algorithms, the one that can look at factorization, and which is one of the key things in one of our security features. That being said, there's also something called post-quantum cryptography, right? And that's using those same systems to come up with cryptographies, algorithms or designs to be able to protect against those kind of things as well too, right? As you mentioned, we can now calculate very large numbers. We can probably do the same thing with these, right? And calculate this quantum cryptography in a sense. So there's a lot of research already doing in that, both from the classic systems and the quantum, because you got to think about, quantum computers are here, but you can see that we're not storing data. They compute, they're qubits. You do calculations, you read the results, and you're back on your classic system. That data you have to store somewhere, right? Now, where's your data being stored, right? It's not just, where's my data actively. Data at rest also has to be protected. So again, that goes back to your plan. How do you protect that kind of data? How do you encrypt it? These kind of things. So having the right plan is usually the best way to do it. I know at IBM we have global business services that's their focus: cryptography, security. Right? IBM is always big at pushing being secure, right? So they're always on top of this stuff. Obviously, they're working with us as well on these systems. They're looking at what kind of aspects can we use to be able to protect and offer protection using classical systems, or using this hybrid of classic quantum systems to be able to compute and be able to do those things.
Last question? I think we have coming short. We're out of time. So just a second, after the talk, we're going to have you at there's a table over there with a separate view, so you can ask questions, take a picture, or anything you want.
When you're talking error, are you talking accuracy? Because I'm concerned about all the errors that we're hearing about, the comparison maybe between
Yeah, so I guess, so if you think about it, and it's on accuracy, because when you take a reading, all right, when you measure it, it's, I want to see, okay, I've done my algorithms, now I want to take a measurement because I want to see what those results are, and I bring them obviously into my classic computer and do them. So if I'm in, error means that when I do that measurement, as I mentioned here, I'm collapsing it to one of two states, 0 or 1, right? So if I know that I'm in a perfectly, linear aspect of maybe either being right in the middle, I know it's going to be 50-50 chance it's going to be either 0 or 1. So if I have 2 qubits, I know that they're either going to be 0, 0, or they're going to be 1, 1, right? But when I take my measurement, let's say on a simulator that has no errors, I'm going to see 50% 0, 0, 50% 1, 1, and nothing with 0, 1, 1, 0. When I do that on an actual machine, what I'm going to see is 0, 0, some on 0, 0, some on 1, 1, and then I'm going to see just a few in 0, 1, 1, 0. Right? Not a lot, but just a few, because it was a simple algorithm, right? But if I do more things and stretch it out, that 1, 0, 0, 1 is going to come up, so now it's going to be exactly across. I'm going to have exact same amounts of all 4, which doesn't help because now I'm in all states and I can't differentiate things, right? So that's what I mean by the error rates, that it's on those measurements. I should be getting 0, 0, 1, 1 because they're entangled. But one of them, maybe when it collapses, it's not collapsing to 0, it's collapsing to 1 because of that. So that's those errors.
So can we give everybody, Robert, a big